Well, hello everybody. Welcome back for the afternoon session. Um, we have a guest speaker on Zoom, uh, Craig Underwood, who is from Surrey University, and he is going to talk about space-based power. So, Craig, if you want to go ahead and share your slides, and the floor is all yours.
Thank you very much, Ian, and good afternoon, everyone. So welcome to this talk. So let me just share my screen and away and hide that.
Yep, that looks fine, Craig.
Great. Okay. So good afternoon, everyone. Welcome to this presentation. As Ian said, I'm Craig Underwood. I'm emeritus professor actually at the University of Surrey, and it's my pleasure to present some of our work on solar cell technology and space-based solar power. So, just a little bit of my background. I've been here at Surrey now for coming up to 40 years. I first came involved with the UOSat satellites, good old Oscar 9 and Oscar 11, when I was a school teacher back in Scarborough in the early 1980s, and setting up a ground station there and using that with my students. Through that, I got involved in satellites in education and working in the ground station, as you can see in the picture there at Surrey. And then because of my physics background, I got involved in the actual design of the spacecraft. So I used to do all the thermal design and all the radiation protection of the SSTL Surrey spacecraft. My research was mainly about sensors, looking first of all at radiation and then optical and radar type sensors, and also looking at the systems of spacecraft, including, of course, the power system. So I formally retired in 2019, but anyone who's ever tried to retire will find they're busier than ever. So life goes on. At the Surrey Space Centre, which is the academic side of the University of Surrey, it's different to the company, spin-out company SSTL. We've done a number of missions in recent years, all based around CubeSats. In fact, all based currently around three CubeSats, starting with Strand 1 in 2013. And our last mission was actually a big satellite, which SSTL built for us, and that was Remove Debris, which some of you will have heard about, I'm sure. But today I want to focus on a mission we did in 2016, which is called ALSAT-1 Nano. And this was a satellite built as part of a know-how technology transfer program with Algeria, and it was paid for by the UK Space Agency. And as sort of quid pro quo for that, it flew 3 British payloads. The payload I'm going to talk about is the solar cell payload, but first of all, a little bit about solar cells, or what we scientists tend to call photovoltaic cells. Of course, they've had a long history in space. In fact, when silicon solar cells were first produced in the sort of 1950s, they were so expensive that really only a space program could have possibly afford them. And so, of course, they saw very early use in spacecraft. And so through the 1960s into the 1970s, and actually, in some cases, even today, silicon junction solar cells are still used. But in the 1980s, we had the so-called 3-5 semiconductor, compound semiconductor solar cells based on indium phosphide and more commonly gallium arsenide. And then multiple junction cells started to appear, first dual junction cells, and today triple, and actually even quadruple junction cells. And throughout that time, the efficiency of solar cells has got greater and greater and greater. When we started with the UOSATs, we flew silicon cells at 12% efficiency, and today typically we will fly triple junction cells at about 28% efficiency. And that's been achieved through using a sort of sandwich technique where the different semiconductor junctions are picking off different parts of the spectrum of light. And so we can use more of the sun's light to generate electricity photovoltaically. Well, while that's all been going on for space, in the terrestrial world, there's also been a revolution in solar cell technology, driven by the net zero race and the urge to go green. And one of those developments has been the development of what we call thin film solar cells. Now, in these kinds of cells, we use quite complicated chemistry to make a very thin layer which can be laid down on a substrate. And that substrate could be a plastic film, or it could be extremely thin glass, so thin that it's actually flexible. And this makes it a very cheap process because it can be printed almost like printing on a piece of paper. And so the cost per watt is very much reduced. So the Centre for Solar Energy Research, now at Swansea University in Wales, and ourselves here at Surrey, we got together to work on adapting this technology for use in space. And the idea was to see if we could make a technology available for use in space that was far cheaper in terms of dollars per watt or pounds per watt than hitherto was possible. So we were sponsored by the EPSRC, by the Engineering and Physical Sciences Research Council, and we worked with industry. We worked with a glass company called Colloquium, who make the cover glass for solar cells in space, and we use their glass as a substrate for printing our solar cells on. And we also worked with SSTL as a potential customer for this technology. So the key innovation from the group at CSER in Swansea was that they had the facilities to lay down what's called metal organic Kappa vapor deposition. So essentially, you can put a substrate in a reactor and then expose that to a gas, and the gas lays out on that substrate over time, and layer by layer you can build up the multiple layers that form the semiconductor material. And the material they were using is cadmium telluride. And in fact, to make it work, you need several different kinds of compound. So we start with sort of conductive layer. We have cadmium sulfide, cadmium zinc sulfide, cadmium telluride. So this very complicated chemical sandwich is gradually built up, and it forms a junction which can then act as a photovoltaic source. Well, the glass that we used was incredibly thin. We asked Colloquium to give us essentially the thinnest glass that they could easily make, and that turned out to be about 100 microns. So what's that? About a tenth of the thickness of a human hair, something of that order. And it's so thin that it really is like paper. It can be bent very over a great radius, so it's a very flexible material. So the advantage of this technology is it's low cost. It provides a potentially very large area solar cells, because you can print over a large area depending on the size of the reactor. But the key parameter for us is cost per watt, but also what we call specific power. That is, how many watts of power do you get for every kilogram of solar cell you fly? And I'm sure many of you know that every kilogram we put into space costs us an absolute fortune. Typical cost for a kilogram to orbit is of the order of $20,000 to $30,000 normally. So for space engineers, weight is everything, and we try to get the lightest weight possible solutions to all our engineering problems. And the cost is good too. So the final costs of this technology is something like a fifth of the cost per watt that we would get associated with traditional solar cells. But the specific power of these solar cells is fantastic. So the cells that we were manufacturing had a specific power of 0.65 kilowatts per kilogram, which is an enormous figure. Compare that with the best efficiency triple junction solar cells. It's nearly double the specific power that's available from them, even though the efficiency of triple junction solar cells is much, much higher than the efficiency of the cadmium telluride cells that we were working with. So 36% for the very best for triple junction cells against 14% that we had then. Although it has to be said that now we're closer to 20-25% with the cadmium telluride technology. Now, solar cells, like all parts of a spacecraft, see a very hostile environment as we launch into space. The act of launching itself is is the roughest possible ride. You have phenomenal vibration, phenomenal forces acting as you accelerate into space at tremendous rate, but also you get the shock from the staging of the rocket, and that's done explosively, and typically the shock that's carried through the structure of the rocket into your satellite, and therefore into your solar panels, is of the order of 1000 G. So it's a bit like taking your mobile phone, holding it at shoulder height and just dropping it onto concrete, which I don't recommend that you do. So obviously we needed to make sure that our solar cell technology was very tough to be able to withstand that, and to be able to withstand the extreme thermal cycling that we see in space, and also the extreme vacuum conditions. So in sunlight, of course, we get the full blast of the sun's rays. There's literally nothing between us and the sun. And at Earth's distance from the sun, that's at nearly 1.4 kilowatts per meter squared of heat flux, essentially, coming into the solar panel. But when we're pointing away from the sun, pointing at deep space, all we see is about 4 Kelvin, so about minus 270 degrees Celsius space. And so the outside of a spacecraft is subject to extreme cycling. In fact, I put a little plot at the bottom there, which is real flight data from good old USAT-2, Oscar 11. And you can see that in our sun-synchronous orbit, about just about 100 minutes, you're getting down to about minus 35 and up to about 12 degrees C just going around the Earth. So one thing that we did is what's called a pull test. You literally use sellotape, Scotch tape. It's an industry standard test across the world. You put the sticky tape over the cell and then you pull it off. And what you hope doesn't happen is that any of the solar cell comes off with the tape. So that's a pull test. We also did thermal shock testing, and we also did mechanical vibration tests as well. Now, the thermal shock is extreme. You heat it up to 80 degrees Celsius, so nearly getting on towards the boiling point of water for 1 minute, and then you plunge it into liquid nitrogen. So liquid nitrogen is minus 196 degrees Celsius. So the shock from going instantly from 80 degrees Celsius to minus 196 Celsius is extremely violent. And again, we hold it for a minute, we pull it out, heat it back to 80, and we keep doing that 20 times. And if it survives that, then it survived the test. So as you can see, the testing is extreme, but we have to do that to get materials that can survive the space environment. At Surrey, we have very good facilities for looking at the microstructure, almost, actually down to the atomic level. And here you can see some photomicrographs of the structure of the different layers inside the cell. This was done by X-ray techniques and electron techniques. If you look, it's very sort of lumpy and bumpy. In fact, it's very disordered compared to a monocrystalline solar cell. This is definitely not monocrystalline. Every little bump you can see is essentially a separate crystal. And really, it can be described, I would say, as being chaotic in nature. And that has led to an interesting property that we discovered, which is that it's very robust to ionizing radiation. Normally, when we expose a monocrystalline solar cell, standard space cell, to the ionizing radiation in space, it degrades quite rapidly, actually. And the mechanism through which it's degrading is that the incoming cosmic rays and protons and even electrons cause the atoms of those crystals to be knocked out of their proper location. So they're displaced. And that leads to a quantum mechanical effect, which can trap charge. And that slow charging up of the structures leads to their performance degrading. But I think the reason our solar cells made from cadmium telluride are so robust against radiation is that they're already chaotic, and so they don't get any worse when exposed to ionizing radiation. One good thing about cadmium telluride is that the band gap energy of the semiconductor is quite high, and what that means is it responds pretty well across a broad area of the spectrum, all the way from near ultraviolet to near infrared. So it maps very well, and that's why it's a good material for this purpose. So I talked about the radiation environment. This is a little graphic that shows that, of course, we are bombarded by trapped radiation, the Van Allen belts that were one of the first discoveries of the space program. If we're in low Earth orbit, we keep dipping into the inner Van Allen belt over the South Atlantic anomaly, and we dip into the outer belt, actually, as we go over the poles. So if we're in a sun-synchronous orbit, which is a near-polar orbit, we get the worst of all worlds as far as low Earth orbit is concerned. If we're higher further out into space, say geostationary orbit, then we're in the outer radiation belt, and we get zapped all the time by high energy electrons. And when the sun is particularly stormy, as it is right now, some of you might have seen the aurora the other night, it really populates the radiation belts temporarily, and we get absolutely fried by radiation. So it's something that all of us have to be aware of in designing electronic systems for space. So here you can see the effect of radiation on what we call the current voltage curve of a solar cell. So this characteristic curve is the pattern that you get from a solar cell. This point here is called the open circuit voltage. That is, if you just put a multimeter in volt mode over a solar cell that's illuminating, you'll get a certain voltage, but there's no current flowing because the multimeter has essentially an infinite impedance. So it's just a voltage, and you get VOC, open circuit voltage. The other test you can do is put the multimeter into current mode, which is a dead short circuit, and you get the short circuit current. Now, if you think about it, if you've got current and no voltage, or voltage and no current, in neither case do you get any power, because power is the product of current and voltage. So it's only at the knee of this curve, when you have a voltage that isn't quite as high as the open circuit voltage and a current that's not quite as high as the short circuit current, that you get power. And the way you achieve that is you connect the cell to an impedance that happens to hold it at that knee position. So a key thing about solar cells is that to get them to work efficiently, they have to be matched to a particular impedance. And unfortunately, that impedance changes all the time. And so our best power systems have dynamic impedance matching, and they actually track the maximum power point of the solar cell. So here you can see how gallium arsenide and silicon degrades with radiation exposure, and it's all to do with this displacement that's going on. Now, to actually test this, we put it in a radiation beam here at Surrey. We have a particle beam, and we hit it with protons. So actually quite low energy protons, but we deliberately chose an energy of proton that would cause the maximum possible damage inside the solar cell. This is a simulation of that, but we actually did this for real. And what we found is that the cells were about 100 times more resilient to radiation than conventional solar cells. So to put that into context for you, if we are designing a space mission these days, say in geostationary orbit, to last maybe 20 years, these cells would last 2,000 years. So that's very encouraging and good news for us. So obviously we wanted to get some actual flight experience, and just by fortuitous chance, at the same time we were working on that, Surrey and Swansea, we were simultaneously training Algerian engineers with the AMSAT-1N mission, a little CubeSat mission, and that would carry 3 UK payloads. So Swansea put in a bid to fly one of their solar cells. Oxford Space Systems put in a bid for their boom, and the Open University put in a bid for the camera, and they were the 3 winners. And so we got to work on putting together a flight payload, which we call the thin film solar cell experiment payload. So at Swansea, they manufactured a set of test cells for us, and although it looks like one sort of little black patch, there are 4 1 centimeter squared cells in that patch, and they had to lay down all the gold contacts so that we could get electricity out of the cell, etc. And I did the electronics, because I've got experience of doing this sort of thing in previous missions, in fact going back to USAT-4 and USAT-5. And so using a microprocessor controlled system, microcontroller controlled system, I was able to put together a circuit to measure the IV curves actually in space, and to measure the temperature, and to do that with extreme precision, so 12-bit precision. And so we get very good, if it worked, we get very good flight data on their performance in space. So there's the little board. And of course, being a CubeSat, all this had to be squeezed into a PC-104 board, which is roughly 10 by 10 centimeters. Well, this is the IV curve that I was just discussing, and there's the maximum power point. You can see that at that point we get the biggest area of that rectangle, which is the biggest power. So with the 4 test cells, we used solid state switches to switch each one in turn. And then I made up some instrumentation amplifiers to measure very precisely the voltage and current and connected it to a programmable current sink. So in other words, the circuit demands a current, the solar cell tries to give that current, and then we measure the voltage and the current simultaneously to check its performance. And before flight, we tested them at Swansea using proper solar simulating light sources. We can use what's called AM 1.5, AMS 1.5 lights, which represent the sunlight levels on average on Earth, and AMS 0, AM0 lights, which match the sunlight intensity in space. And of course, the AM0 lights have a lot of ultraviolet light in them as well, because of course it's not absorbed by any atmosphere. So we measured the efficiencies, etc., and here's the IV curve actually measured for those cells. And then that was delivered to me at the Space Centre here, and I put that together. This is the one of the solar panels on the CubeSat and the test cells there. I used a standard torch, quite a powerful one, to test it just for functional testing. And then when it was all wrapped up and ready to fly, we took it out to India and launched it on a PSLV launch vehicle. And so on September 26, 2016, it was launched into a sun-synchronous orbit, so about 700 kilometers altitude. And in fact, all the payloads worked. So Oxford Space Systems worked. There is the boom deployed as imaged by Open University's camera. But certainly the solar cells worked. And this is the first flight data. So if you see, there are 4 curves there, and they're very close together, which is a good thing. It means all 4 cells are working and tracking together. And there's the open circuit voltage at about 0.95 volts. And there's the short circuit current at about 25 milliamps for a 1 centimeter squared area. Well, over the years, we've seen it change. We've seen it degrade, and that's been very interesting to watch. And the other thing is that AMSAT-1 was designed for 1 year lifetime because the batteries on CubeSats tend not to last very long. We designed it for 1 year. We kind of hoped we might get maybe 1.5, 2 years, 3 years perhaps out of it. But actually, we got more than 6 years. In fact, in the end, I think we got over 7 years of design life out of it. And the payload carried on working. So we got way more data than we expected. In total, over that 6-year period, we got 150 surveys, 30,000 orbits worth. And as you can see, year by year, the curve goes down. So the open circuit voltage drops and the short circuit current drops as well. And the curve also gets flatter and flatter. None of this is good, by the way. It means the efficiency is dropping down. So we wanted to know why. What was it about being in space that was causing that degradation? Well, first of all, I asked the question, is it my circuit? So my circuit had built-in auto-calibration by measuring resistances, etc. And you can see it's perfectly linear and remained perfectly calibrated. So it wasn't a measurement fault. The measurements were accurate. So what could it be? Could it be temperature? So we measured the temperature with temperature sensors under the cells. And there in the blue dots are the degradation in efficiency. And in the red dots are the temperatures when we measured those degradations. And you can see that the red dots are scattered. So in other words, there's no correlation with temperature. It's not a temperature effect. In fact, the temperature effect shows up very nicely as an expected slight linear drop. Solar cells, when they're hot, are not quite as efficient as when they're cold. And so that's to be perfectly expected. We also checked if the fill factor, that's basically how rectangular the shape looks, varied with temperature, and it certainly didn't. So the conclusion was it's not temperature. So what else could it be? Well, if you look at a model of a solar cell, it's modeled as a current source, a photocurrent source, a diode, because it is a PN junction after all, and it's got impedance. It's got a a shunt impedance, a parallel impedance, and it's got a series impedance as well. So you could model that as two resistors. So this is not an electric circuit. This is an electrical model of what a solar cell is like. So if these impedances change, the behavior of the cell will change. And in fact, what we can do is we can look at the change in behavior and find out how these impedances are changing. And what we discovered is that the series resistance isn't really affected much at all, which is a good thing. But what we did find is the shunt resistance was dropping. And that's a bad thing. If it gets less and less impedance across the cell, it means that there's a bypass of the current and we don't get that power coming out of the cell. And in fact, it was exponential pretty much in time. And that was interesting to observe, very clear signature. And it wasn't to do with the space environment. What it was to do with is the fact that to do the experiment and get it ready for flight in just a month or two, we had to make some compromises. And one of the compromises we had is we couldn't change the electrical contacts at the back of the cell from gold. We had gold contacts, and we knew that in the space environment, that gold could become mobile. So atoms of gold could leave the electrical contact and migrate into the cell. And that as they did so, that would form a conductive path through the cell and effectively short out the shunt impedance. And that's pretty much what we saw. So it fitted very well with other observations from other tests that had been done on cells over the years. And indeed, we kind of knew that that might be a possibility before flight. So in the future, we would have different systems on board. So what are the next steps? Well, we'd like to fly it all again. Next time, flight with a proper back contact. We'd have to make a different kind of metal back contact. And also, we'd like to try what are called concentrated cells. The picture on the right there shows a Fresnel lens over a solar cell. It turns out solar cell material is quite expensive and lens material is quite cheap. So it actually is cost effective, although a bit heavier, to actually have a lens focusing the sunlight onto a smaller area of solar cell. Of course, you get a much greater light flux on that area, and you can actually get way more power out of the cell that way. But there are all sorts of issues. You've got to have the optical alignment has to be right and so on. But we want to try that in space. And so I've come up with another version of the thin film solar cell experiment called ASCOT that I hope to fly in a couple of years' time. And what I would like to do is fly Swansea's cadmium telluride cells again, but also fly cells developed by my colleagues here at Surrey, Jay, who's producing a material called perovskite. Perovskite is a sort of copper compound, and it looks very promising, but it's not really had much flight heritage in space yet, and there are some issues with it that we think we might be able to solve. And also, I'm in contact with the University of Cambridge, with Louise's group there, and she's working on thin film gallium arsenide cells. So the ideal for me would be to fly all these technologies together and get comparative data on their performance. And also, we'd like eventually to unroll these solar panels in space. So instead of having deployable solar panels that are rigid, we just simply unroll them. So why are we interested in thin film solar cells from a space point of view? Cheaper, better specific power, but that leads us to be able to have much, much bigger solar arrays so that we can generate much more power. And there are so many applications in space that need huge amounts of power. I mean, communication satellites these days typically have powers in the tens of kilowatts. So they already have big but rigid solar panels. A space station has got about as much electricity as a sort of hospital or something like that. It has very big but deployed solar panels. Actually, they're not rigid on that one. Moon bases, bases on Mars. But the one that I want to talk about is space-based solar power. So it sounds a bit science fiction, doesn't it? And in fact, it started in science fiction with Isaac Asimov in 1941, writing one of his short stories about robots. And his robots were tending a space-based solar power station. So a power station in orbit using sunlight to generate electricity and then beaming that electricity down to the planets. He doesn't say explicitly, but we might assume it was using microwave power. Now, this was taken quite seriously by NASA, and so a gentleman called Peter Glaser in the 1970s studied it very carefully for NASA and found it was quite feasible. We had the technology even then in the 1970s to generate solar power in space and to convert that pretty effectively into microwave energy, beam that microwave energy to somewhere else, and then rectify that microwave energy back to AC electricity again, or actually DC electricity, and use that to do something. In fact, an experiment was done with the Goldstone antenna, one of the Deep Space Network antennas, where they did exactly that. They connected solar power to it. They powered the microwave transmitter on the antenna, and they beamed power to a mountain, I think a few miles away, and then they converted that to light up some car headlight bulbs. Today, we can do this way more effectively because we have gallium nitride and other very high efficiency semiconductor-based amplifiers. And so we have a very good conversion efficiency from light to electricity in the solar cell and from electricity to microwave in the amplifiers, and then out from microwave energy back to DC electricity in what's called a rectenna, a rectifying amplifier. So the technology is there, but it was never practical because it would just cost too much. And certainly in the 70s, we couldn't really build the infrastructure in space. And even in the 80s with shuttle, we couldn't do it really practically. So it's been looked at decade after decade. But the drive now is the green agenda. Is it worth looking at it again to see has something changed? And what's changed is something no one expected. And that is private enterprise in space. So through companies like SpaceX and Elon Musk, the cost of access to space has dropped absolutely phenomenally. And with the Starship coming along, we are talking now about $1,000 perhaps per kilogram, as opposed to $20,000 or $30,000 per kilogram. And that's the game changer. Because if we can get the costs of every kilogram down that way, we can afford to launch the tons and tons and tons of material that would be needed to construct a power station in space. In fact, to construct many. And now China, India, Japan, the UK and Europe also are looking at this very seriously, as indeed are the Americans again. And Britain is, in terms of climate change and net zero, is doing well in a way. We have been one of the first countries to simply get rid of all our coal. And I shed a tear the other day because I actually worked at Ratcliffe-on-Soar Power Station and I saw it built. It came on stream in 1967. I remember watching it being built. It was not too far away from where I lived. And I went to work there in 1979. And so I have a sort of fondness for a particular boiler on that power station. But it's no more, and there is no more coal burning power stations in Britain. But we want to get to net zero by 2050, and that means getting rid of carbon from our electricity generating plant by 2035 is what the government are talking about, although some people are talking about trying to do it by 2030. Well, this is going to be a huge challenge because right now what we've done is we've filled the gap with natural gas. Natural gas can be burnt in a turbine, produce electricity quickly, and it fills in the gaps when the sun isn't shining, when the wind isn't blowing, or when the wind is blowing too rapidly. And at the moment, we're getting away with it because we're buying more gas. But rather crazily, in my view, we've got rid of our own gas mining. So what we're doing effectively is we're buying in very expensive energy. So these graphs here show you why renewables themselves are not a complete answer. They are important, they're part of the answer, but they can't ever be a complete answer because they're not reliable. You can't have power when you need it. There are times when the wind doesn't blow, and that's shown here, and it has to be filled in by what we call baseload power. And up to now, that has been coal, some nuclear and mainly gas. Now it's going to be tiny amount of nuclear and mainly gas, but our nuclear power stations are at the end of their lives too, because we haven't invested in them. And so now we're going to have to start building them again, and it's going to be very expensive. So we've gone from a net exporter of energy here in around about the turn of the century. We were still exporting energy to Europe. Now we buy our energy in very expensively. And here you can see our installed capacity in terms of power and in terms of energy and how it compares with what we actually use. So people get very confused about gigawatts and gigawatt hours. They're not the same thing. One is a power, which simply tells you the rate at which you're using electricity. What's important is energy. So you can see if we add up those numbers there, we're of the order of 100 terawatts hours of energy is potentially available from our renewables, but we need 340 terawatt hours permanently. So to get that, we need to at least triple, and because the population is growing, probably quadruple or quintuple the number of wind farms, the number of solar array farms across the country, which means getting rid of our agriculture and vying with land usage with everything else we want to use the land for. So the previous government asked again, is it possible that we might do this not by building solar farms on the ground, but by putting a solar farm in space and beaming the power? Would that make any kind of sense? It sounds implausible, but so they asked Fraser Nash to look at it, and they did. And they did a complete study, literally a system end-to-end study, including all the national grid aspects and the actual practical delivery. And astonishingly, they found that it was not only feasible technically, but it was actually a cheaper way of providing baseload power than the current methods, including nuclear. And so they took for their basis a power station that can produce 2 gigawatts direct to the national grid. So that's about the same as a typical coal-fired power station. And it's a lot of electricity. And to get 2 gigawatts delivered, you need to generate 3.4 gigawatts in flight and beam that down with microwave energy, actually just in S-band. And the rectenna on the ground would be similar in size, just a little bit smaller than a wind farm. So here's one, for example, in the Thames estuary we might propose. Now, people worry about radio beams. People, worry about mobile phones and phone masts, which they don't need to. The energy in this beam, the energy density is quite low. It's 245 watts per meter squared. In other words, it's about a quarter of sunlight. So it doesn't have any consequences for birds and animals and humans, even if they were exposed to the beam. And the beam, of course, would be controlled. So they looked at 3 systems: the British system called Cassiopeia, due to Ian Cash; an American system called SPS Alpha, due to John Mankins; and the Chinese system called MRSPS. And they all have different characteristics. I'll talk about Cassiopeia because it's an interesting thing. It would be 2,000 tons. The antenna itself would be a phased array antenna, 1.6 kilometers across. These are huge numbers. And the rectenna on the ground would be 5 kilometers across. But actually, it's very simple. It's kind of wire and dipoles. It would be transparent to light. This is it. It's a wonderful system. It's going to be very complicated, and there's a lot more work to be done on it. But essentially, you've got a phased array that steers the beam, so the beam is always pointing at the rectangle, and you've got these solar cells shown here as little dots. I think they probably won't be like that in the real thing. But that's Ian's design. It's very clever, but I think it's going to have some challenges. John's, by the way, these are the mirrors that direct the light on. So the whole idea is that the light from the sun is always directed and the beam is always controlled to point down at the Earth. John Mankins' idea is more conventional. It's got steerable mirrors, they're known as heliostats, but it's similar in size because the physics just drives you to these sorts of sizes. A bit heavier, 8,000 tons. Everything else about the same. The Chinese design, this one is really like an overgrown communication satellite, The challenge there is going to be how do you get gigawatts of power through a rotating joint? But this is even heavier, so it's not the most efficient system, though to be honest, they have other designs which are better. Anyway, Fraser Nash did the study. The British system actually came out slightly better than the others, but there's not a huge amount between the American and the British design. But this graph is interesting. Look at the cost of first-of-a-kind nuclear power. That's what we call the levelized cost of electricity. And you can see that space-based solar power is much less. So that's the thing to compare to, because this is the baseload power. Yes, the electricity from renewables is relatively cheap compared to these, but that's not the point. The point is we're replacing the baseload. We'll still have the renewables in the ground, but we're replacing the baseload. John did the same analysis independently in America and got the same result. So we've set up a space energy initiative to look at this. I sit on the technical committee for that. The previous government went out to places like Saudi Arabia to get them, investment, and there was strong interest to invest in the UK to get this going. And out of the Space Energy Initiative, a company called Space Solar has come, and now to Fraser Nash, which is now actively working towards this goal of demonstrating a first-of-the-kind big station like this by sort of 2035 is what we hope. Europe is just about getting its act together. They're doing paper studies, but they're also interested now. China, you might imagine, is not only doing paper studies, they're doing actual physical experiments. They say they will do a first-of-a-kind experiment in space in the next year or so, and I would believe that they're pushing ahead in space technology so fast compared to the West. And Caltech, my colleagues at Caltech in America, have actually demonstrated a bit already. And they launched a really neat experiment to test new solar cells and to test deployables. This came from my colleague Sergio Pellegrino. And you can see it there all unwrap from a compact form. And that's how it would deploy in space. And that actually worked in orbit. So congratulations to them. So got like 3 minutes maybe for questions, but thank you very much for listening. I'm happy to take any questions.
Okay. Craig, thank you very much. If we can give him a round of applause, because I don't know about anybody else, but I find that very interesting. And so, yeah, we do have about 3 minutes. So does anybody have a question?
Hi, Craig. Very interesting. I was just curious, what do the necessary orbits look like to have this thing, in sunlight and also in sight of this rectangle on the ground?
Good question. I should have said, of course, the main one that we're considering is geostationary orbit, because, of course, the ground is always in range then. And when you really think about it, because the geostationary orbit is in the Earth's equatorial plane, it's tilted with respect to the Earth's orbit around the sun by 23.5 degrees by the obliquity of the ecliptic. And that means that except for 90 days of the year, it's in sunlight 24 hours a day. That's why it's baseload. So it's permanently lit. And only around the equinoxes, around the spring and the autumn equinoxes, do you get any eclipse at all. And the longest eclipse is only 72 minutes. So for that, you could just then switch to another power station just slightly at a different angle and get the baseload power. Probably the first experiments will be done in low Earth orbit, and it would be much less power. It would be a demonstration kind of mission. And we've also considered intermediate orbits where by a small constellation, we can provide power from one spacecraft into Europe and then into America and then into China and then back into Europe again. So there are a number under consideration, but GEO is the main one, I would say.
Okay, thank you very much. Next question.
Yeah, just a quick one. So why 2.4 gig band was chosen? That's the maximum of the water absorption, as I know.
I'm sorry, because you're away from the microphone, I didn't quite catch that.
Yeah, I'm asking why 2.4 gig band was chosen, because that's the maximum of the water absorption.
Why 2.4 gigahertz?
Yeah.
for the study, just because it's one of the available frequencies potentially for this. In fact, the frequency now being considered is closer to 5 gigahertz. So that was just for the purposes of the study.
Okay, we're running to time, but I think we'll try to take a couple more questions at least.
Do you have a figure for end-to-end efficiency of a space-based system?
Yes,
sunlight to
though
grid.
I can't recall it directly from my memory. But I basically gave you the end-to-end efficiency in terms of the power. So by generating 3.4 gigawatts in space, we get 2 gigawatts delivered to your house. So it's pretty high.
Hi, Craig. A slightly off the line question. How does it compare with, for example, getting 3 large systems in the desert, which will be permanently illuminated, and then shipping the power around the Earth without actually doing it from space? Why do it from space when you could do it on the Earth, in other words?
I'm sorry, because again, you're away from the microphone. I couldn't quite catch that. Why are we?
Why do it in space when you can do it on the ground if you were to put some stuff in deserts that would give you 24?
Because we have something called the day-night cycle. So for half the day, the sun doesn't shine, and also we have clouds. So actually, for all the power installation in Britain for solar arrays, you can only ever get 10% of it. Potentially.
Yeah, my question didn't quite come out, sorry, Craig. The idea was to have them distributed around the globe, around the places where you do get good sun.
The satellites would be distributed around the globe, yes. So there would be, it's, by the way, it's dispatchable power as well. So the beam can be switched very rapidly from one place to another. So, for example, it could be powered into Europe at night when we need it. And then in the daytime, it can be diverted to somewhere else.
Okay, next question.
Given the number of things wanting to occupy geostationary orbits, has someone done a number for sort of how many of these massive structures you could fit in the geostationary plane? So
I think your question is, what about the overcrowding of the orbits? Yeah, it's an issue. And in fact, one of the environmental impact studies that is underway is looking at that, because these are big structures. Obviously, roughly speaking, we're talking about an object which is the size of a small city. It's 5 kilometers by about 2 kilometers across. So yes, it's that's going to be one of the issues for the use of geostationary, and also, of course, getting the frequency allocation agreed internationally is an issue. But also, we don't want the VHS Betamax problem. We want all the systems out of China, America, Europe, India to be compatible with each other, so that we can all share the power as well. So that's a legal thing. It's already under discussion with the United Nations to try and get that sorted out.
Okay, we're running a little over time, but I think we'll take one last question.
Hi, Craig. Thank you very much. Very interesting talk. Thinking back to your cadmium telluride in-flight experiments,
Yeah.
and you found you had a degradation of output power over time. Reminds me of a case we had, must have been in the early 2000s, of the problem where cover glass for the solar cells was glued on, and the glue turned opaque in space. I don't know if you remember those cases, but yeah,
I don't remember them, but I can well believe it. It is an issue,
it was a major thing, and there were three geo satellites affected by it. I wondered if it may have played a part in your tests at all.
No, you see, well, the testing showed that it was the shunt resistance that was changing rather than any other form of degradation. We very carefully modelled all the different ways it might be changing, and that's the one that fitted the best. We used proper space-rated glue, but it's a very interesting point, because there are a number of companies at the moment who are trying to do space cells on the cheap and use terrestrial type glues and terrestrial type solar cells, and I'm not sure they're really aware of those kinds of issues, because they definitely are there. So yeah, you can be caught out. But actually, my colleague Stuart did very careful analysis of it, and as far as we can tell, it's the gold migration fits the degradation scene best.
Okay. Once again, Craig, thank you very much, and thank you for spending an extra 5 minutes answering questions. And hopefully you'll come back and give us an update at some point in the future. So if we can show our appreciation once again to Craig.
Thank you very much.